Okay, now I want to talk about laws of large numbers. Weak law of large numbers first. Let x1, x2, and so on be IID with finite first moment. Okay, the expectation of x1 to be mu. And as n goes to infinity, the sum of xi's divided by n converges to mu in probability. Okay, so that's the weak law when we say the convergence in probability. The same setting can be said as strong law of large numbers. When we say almost sure sense convergence. And we have autonomous sense convergence. In this textbook, we will use weak law of large numbers mostly. In some chapters, we will use strong law of large numbers as well. So this one is used more often than strong law. This one will not be used in this textbook. But you can have this as a reference. If you know this, there are some difference between these laws. It would be helpful for you in the future. Now I want to talk about surface hardening. A high-dimensional cube, interval -1 to 1, and nth cube, nth dimensional space, is almost the boundary of a ball. So this is very intuitive statement. It says that when you consider a norm of high dimensional vector of dimension n, that norm lies somewhere on the surface of a ball, as this figure talks about, figure indicates. So the norm of a vector lies somewhere on the surface, a little bit beyond the surface or inside the surface. Not too much outside of the surface, but not too much inside the surface either. So not inside, not outside, but on the surface. That's the key concept. So what do you mean by surface? That's the norm of a vector. So let's consider this random variable. Let x1, x2, and so on be independent, uniformly distributed random variable on the interval -1 to 1. So let's take a look at that one. All right. So in this case, it's a uniform distribution. So xi is a uniform distribution. So the length of the interval is 2. So it is half. right? That is the PDF of this distribution from small x running from -1 to 1. Okay, so and the 0 outside of this interval. And what is the mean of this random variable? The mean of this random variable is -1 to 1. The PDF is half, and you multiply with the value x and integration. So this one is half x squared over 2 -1 to 1. So 1 minus 1 is equal to 0. So this should be equal to 0. So expected value of x is 0. What about now expectation of x squared? So we have to do this now, and I have to have a 1 over 3. What is this one now? That is 1 minus, oh, I forgot about taking the third power. Okay, so it should be the third power. So the numerator goes 1 minus -1. So it is 1 plus 1 at the numerator. So the numerator is 2. That should be cancelled with 1/2 in front. So the second moment should be 1/3. So that's the second moment, which is 1/3. Okay, so that's the second moment. Now, let's consider weak law of large numbers. Weak law of large numbers says this sample power, xn squared to xn squared divided by n. So that's the average power. Should converge to second moment in probability as n goes to infinity. So that is true if we consider each IID random variable. The power is 1/3, so that should be true due to the weak law of large number. Okay, now we consider n-dimensional random vector x, x1 all the way up to xn, and its length is nothing but square root of sum of xi's. Okay, thus for each epsilon greater than 0, you can always find a large enough n such that probability that this norm square divided by n deviates too much from 1/3 is equal to 0. That's due to the law of weak law of large numbers. Because this one converges in probability, that means this should be true. So having said this and writing this in different expression like this, give a little and take away little from the ratio, we can also write this in terms of norm. So in terms of norm, give a little and take away little, probability of such event is equal to 1. So probability of all those n-dimensional vectors that belongs to this event should equal to 1. That is exactly what is meant by this picture for three-dimensional case. So here is the norm of this random vector, and give a little bit, take away a little bit, then the probability of a three-dimensional vector lie inside this region is equal to 1. As we let n goes to infinity, surface hardening occurs. Okay.